So next up, let's take a look at operations on algebraic vectors in R cubed, or in 3 space. If we let vector A have components A1, A2, A3, and vector B have components B1, B2, and B3, if we are going to add vectors in 3 space, all we need to do is add the x components, so A1 plus B1, add the y components, A2 plus B2, and add the z components, A3 plus B3 together. If we're going to subtract vectors in 3 space, we just subtract the components. So we have A1 minus B1, A2 minus B2, and A3 minus B3. And finally, if we multiply a vector by a scalar, all we need to do is take each of the components and multiply them by that scalar. So we have Ka1, Ka2, and Ka3. Let's take a look at a few examples incorporating these operations. So example 1, if we let vector A equal negative 1, 2, and 3, and vector B equal 4, negative 5, and 6, let's determine 3A minus 4B. So that would be 3 times negative 1, 2, and 3, minus 4 times 4, negative 5, and 6. First of all, we're going to multiply the scalar by the vector. So we have negative 3, 6, and 9, minus 16, negative 20, and 24. And if we subtract those two vectors, we end up with negative 19, 26, and negative 15. So that is 3a minus 4b. Part B wants the magnitude of this vector. So we want the magnitude of negative 19, 26, and negative 15. So that means we're going to take the square root of negative 19 squared plus 26 squared plus negative 15 squared. You should end up with the square root of 1262. For this next example, we're going to revisit our special unit vectors, I, j, and a third one, vector k. So remember, I follows the x-axis, so vector I is now defined as 1, 0, and 0. We're going to incorporate the z component. J follows the y-axis, so this would be 0, 1, and 0. And k, our new vector, will follow the z-axis. So that's going to be 0, 0, and 1. So these are all vectors with a length of 1 and parallel to the x, y, and z axis. So remember, our x-axis points out towards us, the y goes to the right, and the z points upwards. So if I want to rewrite 4, negative 5, and 6 using these special vectors, remember 4 means 4 along the x, negative 5 means negative 5 along the negative y-axis, and 6 means plus 6 along the z-axis. So we can say that 4, negative 5, and 6 is equivalent to 4i minus 5j plus 6k. So those are two representations of vectors in 3 space. So example 3, we're going to go back and revisit collinear vectors. So determine if u and v are collinear. Collinear vectors are vectors that can be translated so that their initial and end points lie on the same line. Or that means when they are arranged tail to tail, the angle between them is 0, so two vectors that look like this, or 180 degrees. So they're 180 degrees apart, or they're 0 degrees apart. Also, two vectors are collinear if one can be expressed as a scalar multiple of the other, which means that vector u is equal to vector v if you multiply it by some scalar value. So let's look at how do you prove two vectors are collinear in 3 space. So method 1, I'm going to use the definition given above, that vector u is equal to kv. So again, we're going to assume that vector u and v are collinear. And if we do that, then we know that u must be equal to some scalar of v. So we're going to start with a definition. So U equals KV. So remember that U is 15, negative 18, and negative 12, and that's equal to K times negative 10, 12, and 8. So now we have 15, negative 18, and negative 12 is equal to negative 10K, 12K, and 8K. Then all we're going to do is isolate for each of the components. So let's start with the x. We know that the x, 15, is equal to negative 10K. The y component, negative 18, is equal to 12K. And the z component, negative 12, is equal to 8K. And then we're just going to solve for k. So you see for the first one, k is equal to negative 15 over 10, which is equal to negative 3 over 2. K is equal to negative 18 over 12, which again is equal to negative 3 over 2. And k is equal to negative 12 over 8, which is equal to negative 3 over 2. So in this case, since all the k values are the same, then u and v are collinear. So since u, vector u, is equal to negative 3 over 2 of vector v's, then u and v are collinear. So that is one method to prove two vectors are collinear. Here's another method, using a scalar multiple of a third vector. So let's take a look at u and v one more time. If I take vector u and let's say factor out the number 3 from it, I'm left with 5, negative 6, and negative 4. And if I take a close look at vector v and I take out a negative 2, that leaves me with 5, negative 6, and negative 4. Notice that both u and v are collinear to 5, negative 6, and negative 4. And since u and v are both collinear to 5, negative 6, and negative 4, then they must also be collinear to each other. So this is our second method to prove that two vectors are collinear. So try the following questions and good luck.